discussing the preliminaries which are not covered with the presentation, the video presentation that was given to you on the Pursue page of our module. So let's begin with preliminaries. I am using an ebook written by Hudson. It's Abstract Algebra 2013, and I got this from the internet, of course, from other universities of the States, because the book in the library is not that updated compared to the book that I can get from online. So preliminaries, these are the first part of the the book written by Hudson. Let me show you Abstract Algebra Theory and Applications written by Thomas W. Hudson from Stephen F. Austin State University, August 16, 2013. I guess he's using this with his class in Abstract Algebra, and he is also showing this flow chart on how we approach the different chapters of the book. So chapters 1 to 6 are essential. And if you choose chapter 7, chapter 8, if you can finish all that, those are specific. There are no specific prerequisites, but we need to pass some basic information from our previous topics. Okay, so the contents, preliminaries, the integers. So I'm following this book this time. Last year I'm using Galian's book. However, our discussion in abstract algebra will only fall on the preliminaries portion. So I choose this book now because uh, I am thinking that I hope we can really come up with the discussion with the groups, the different kinds of groups, and this isomorphism, homomorphism, symmetry, structure of groups, and the rings, polynomials, integral domains, and fields. Okay, so let's begin with the preliminaries. Again, under this, a short note on proofs and sets and equivalence relations. A short note on proofs. Before that, a certain amount of mathematical maturity, is necessary to find and study applications of abstract algebra. Take note, certain amount of mathematical maturity. Are you matured enough to deal with this kind of subject? Okay. So a basic knowledge of set theory, mathematical induction, equivalence relation, and matrices is a must. So set theory, you have already passed this course. Mathematical induction is discussed in the video presentation, as well as equivalence relations. Matrices were discussed, I think, very well with Sir Cordita in your linear algebra. Even more important is the ability to read and understand mathematical proofs. And this is our problem. Read and understand mathematical proofs. Hopefully, with this course in abstract algebra, you can really master understanding and making your own mathematical proofs. So in this chapter, we will outline the background needed for a course in abstract algebra. Let's begin with a short note on proofs. There are certain terms and concepts here that I want you to absorb because we will be using them for the rest of our sessions in abstract algebra this semester. So abstract mathematics is different from other sciences. In laboratory sciences such as chemistry and physics, scientists perform experiments to discover new principles and verify theories. Although mathematics is often motivated by physical experimentation or by computer simulations, it is made rigorous through the use of logical arguments. In studying abstract mathematics, we take what is called an axiomatic approach. So, we will use axiomatic approach, not the laboratory experiments or discoveries that we do in laboratory sciences, but we will approach it with logical arguments, axiomatic approach. That is, we take a collection of objects S and assume some rules about their structure. So these rules are called axioms. Okay, so how to do axiomatic approach? We take a collection of objects S and assume some rules about their structure. Using the axioms for S, we wish to derive other information about S by using logical arguments. We require that our axioms be consistent, that is, they should not contradict one another. We also demand that there not be too many axioms. If a system of axiom is too restrictive, there will be few examples of the mathematical structure. So let's begin with the first term, statement. A statement in logic or mathematics is an assertion that is either true or false. Sometimes we interchange statement and sentence. Okay? But the statement, when we talk about statement in mathematics or in logic, that statement can either be true or false. So consider the following examples. 3 plus 56 minus 13 plus 8 over 2. All cats are black. 2 plus 3 equals 5. Any observation of these examples? Okay. I hope you have seen that all cats are black is a complete sentence. 2 plus 3 equals 5 is also a complete sentence or statement. And we know that in our mathematics in the modern world, few years back, because we have verbs here which are and equals or is. But in this first example, we cannot find something that will help us decide if this is true or false. All cats are black. Okay, true or false? False. 2 plus 3 equals 5. True. These two are statements. But the example number 1 maybe is not. 2x equals 6 exactly when x equals 4. Okay, 2 times 4 equals 6. Exactly when x equals 4. Is that true or false? If ax squared plus bx plus c equals 0 and a is not equal to 0, then this, what is this? What formula is this? Okay, quadratic formula. X equals negative b plus and minus square root of b squared minus 4ac over 2a. And the next is x cubed minus 4x squared plus 5x minus 6. So this last example has the same case with the first example. What is that case? All but the first and last examples are statements and must be either true or false, except first and last examples. Let's proceed with a mathematical proof. What is a mathematical proof? A mathematical proof is nothing more than a convincing argument about the accuracy of a statement. Okay? Convincing argument. Such an argument should contain enough detail to convince the audience. For instance, we can see that the statement 2x equals 6 exactly when x equals 4 is false by evaluating 2 times 4 and noting that 6 is not equal to 8, an argument that would satisfy anyone. Of course, audiences may vary widely. Proofs can be addressed to another student, to a professor, or to the reader of a text. If more detail than needed is presented in the proof, then the explanation will be either long-winded or poorly written. If more detail than needed is presented in the proof, then the explanation will be either long-winded or poorly written. If too much detail is omitted, then the proof may not be convincing. See that either ways you should be writing enough proof. Not too long, not too detailed, and not too less detailed. Again, it is important to keep the audience in mind. So whether you are writing the proof for another student, for your professor, or reader of your assignment or the book that you are writing, you should keep in mind that it should have enough details, not too long and not too short. High school students require much more detail than do graduate students. A good rule of thumb for an argument in an introductory abstract algebra course is that, okay, rule of thumb, it should be written to convince one's peers, whether those peers be other students or other readers of the text. So, it should be written to convince one's peers. Let us examine different types of statements. So, we are done with statement, mathematical proof, and now the different types of statements. What are those? A statement could be as simple as 10 over 5 equals 2. However, mathematicians are usually interested in more complex statements such as if P then Q. So, this is a statement, but according to Hudson, mathematicians are usually interested in more complex statements. So, if P, then Q, where P and Q are both statements. If certain statements are known or assumed to be true, we wish to know that we can say about other statements. Here, P is called hypothesis and Q is called the conclusion. So, different types of statements. If P, then Q. So, P is a hypothesis, Q is a conclusion. So, consider the following statement. If ax squared plus bx plus c equals 0 and a is not equal to 0, then this one, x can be solved by using the quadratic formula. X equals negative b plus and minus square root of b squared minus 4ac over 2a. The hypothesis is this one, the quadratic general formula. And the condition A should not be 0. The conclusion is the quadratic formula. Notice that the statement says nothing about whether or not the hypothesis is true. However, if this entire statement is true and we can show that ax squared plus bx plus c equals 0 with a is not equal to 0 is true, then the conclusion must be true. A proof of this statement might simply be a series of equations. So this is how to translate the general equation of quadratic, the general quadratic equation to the quadratic formula. So this is the whole process of doing it. If we can prove a statement true, then the statement is called a proposition. So the statement will become a proposition if you prove that it is true. A proposition of major importance is called a theorem. Okay, so every statement that we have proven true, we call that proposition. But if a proposition has a major importance in our field mathematics, then it is called a theorem. Sometimes, instead of proving a theorem or proposition all at once, we break the proof down into modules. Okay, these are the terms that I would like you to remember. That is, we prove several supporting propositions which are called lemmas. Okay, daghana na ma'am. Again, so sometimes, instead of proving a theorem or proposition all at once, we break the proof down into modules. So, unsa man ang modules? Modules is when we prove several supporting propositions. And these supporting propositions are now called lemmas. That means within a module, we have plenty of propositions and we can call them lemmas, and use the results of these propositions to prove the main result. If we can prove a proposition or a theorem, we will often, with very little effort, we will often, with very little effort, be able to derive other related propositions called corollaries. Okay? So, from statement, if you can prove that statement, it can become a proposition. And a proposition with major importance, we call that theorem. Sometimes, instead of proving a theorem or a proposition directly or as a whole or at once, we can divide them into modules. And modules contains a series of propositions that now can be called as lemma. That's why some books use lemma 1, lemma 2, lemma 3. They are still propositions but is belonging to one module. And when we can prove a proposition or a theorem. Imagine a theorem is a much bigger concept. If we can prove a theorem or a proposition, then we can also derive another related propositions out of that big theorem, and we call them corollaries. Okay, so you have statement, mathematical proof, proposition, theorems, modules, lemmas, and corollaries. Another thing that I want to emphasize with you with this topic is this: some cautions and suggestions about mathematical proof. So there are several different strategies for proving propositions. Several different strategies for proving propositions. In addition to using different methods or proofs, students often make some common mistakes when they are first learning how to prove theorems. To aid students who are studying abstract mathematics for the first time, we list here some of the difficulties. Okay? Difficulties that they may encounter and some of the strategies of proof available to them. It is a good idea to keep referring back to this list as a reminder. So for you, aside from having this in your module, I want you to write this in your notebook. So other techniques of proof will become apparent throughout this chapter and the remainder of the text. Let's begin with this one. Let's call this number 1. A theorem cannot be proved by example. However, the standard way to show that a statement is not a theorem is to provide a counterexample. Yeah, I know that you know this maybe already, that we cannot prove a theorem with an example. Okay, but we can prove it by providing a counterexample. So what is a counterexample? An example that would make the theorem false. Okay, that's a counterexample. So if we can make, then you would ask, so if we can make a counterexample, we should supposed to be allowed to make examples to prove the theorem. But it is not how it works in mathematics. We need to use counterexample, because if we can prove that this one is false because of this, then the theorem is true. Oh, so that's how we think when we do mathematical proofs. Next, quantifiers are important. Words and phrases such as only, for all, for every, and for some possess different meanings. So I would like you to recall the lessons that we have in mathematics in the modern world about quantifiers. Only if and only if, for all, for every, and for some. they have different meanings. So I'm sure after this, you will be looking for the right meaning for all of these quantifiers. Next, the third, never assume any hypothesis that is not explicitly stated in the theorem. Yeah, this is one of the problem when proving. We call this sometimes as overthinking. Even if it is not stated in the statements or in the argument, we tend to think that it is true for that matter, and that is not the case when you make a proof. Anything that is not clearly stated in the statements given, whether it's a hypothesis or conclusion, never assume that it exists. It's just the same kanang when we talk about something with our friends and then we ask niunday ko ana, okay, so do not assume, bawal mag-assume sa proving. We should have clearly read what's in the argument, what's in the statement, what's in the hypothesis, and what's in the conclusion. We cannot assume at least unless otherwise stated. So you cannot also take things for granted. If it's there, do not underestimate its existence. Example, something is writing about this one in that statement and you think that it's not that important and you neglect to to include that in your proof, then that is also a different kind of story, which is also a not good practice in proving. So again, never assume. If it's not stated, don't think about it. And then if it is stated, do not underestimate its existence. Number 4. Suppose you wish to show that an object exists and is unique. So you wish to show that an object exists and is unique. What are the things that you need to do is first show that there actually is such an object, that it really exists. To show that it is unique, assume that there are two such objects, say R and S, and then show that R is equal to S. So that's how complicated our life will be in proving. Okay? So, how to show that something really exists and it is really unique? So, to show that it actually exists, you first show that there actually is such an object. Prove that there is an object such as that. And to show that it is unique, you need to assume that there are two such objects. Say R and S and then show that R is equal to S. The previous reminder tells us to never assume, but this part encourage us to assume. That's mathematics. Okay? Assume that. For example, those are normal days of your life to assume. But when you do proving, remember rule number 3. Next, rule number 5. Sometimes it is easier to prove the contrapositive of a statement. So, what is a contrapositive? Can you remember contradiction? The different statements in our logical reasoning. Contrapositive is number 4. So, it is easier to prove the contrapositive. Proving the statement if P then Q is exactly the same as proving the statement if not Q then not P. Okay? So, sometimes we need to use the contrapositive of the statement in order to prove it. Lastly, although it is usually better to find a direct proof of a theorem, this task can sometimes be difficult. It may be easier to assume that the theorem that you are trying to prove is false and to hope that in the course of your argument you are forced to make some statement that cannot possibly be true. Again, although it is usually better to find a direct proof of a theorem, this task can sometimes be difficult. It may be easier to assume that the theorem that you are trying to prove is false and to hope that in the course of your argument you are forced to make some statement that cannot possibly be true. Worse. So remember that one of the main objectives of higher mathematics is proving theorems. Theorems are tools that make new and productive applications of mathematics possible. We use examples to give insight into existing theorems and to foster intuitions as to what new theorems might be true. Applications, examples, and proofs are tightly interconnected, much more so than they may seem at first appearance. So, that's all for the necessary things that I would like to tell you about the preliminaries. Again, we have terms that we need to remember: axioms, statements, mathematical proof, rule of the thumb, different types of statements, hypothesis and conclusion, and then proposition, theorem, modules, lemmas, corollaries, and the quotients and suggestions, difficulties and strategies of proof, which are provided here. And the next part will be sets and equivalence relations that I'm sure have been discussed in the video presentations you have watched since Wednesday. But I will be making another video showing to you what's inside sets and equivalence relations in this book in order to compare with your notes from the video presentation. That's all, and thank you very much.